Yes. Hello friends, welcome to the session, continuation of chapter 5. I am discussing in power measurement, I am discussing electrodynamometer type wattmeter. Okay. In the last session, I discussed about what exactly true power measured by the wattmeter, then what is the measured power. Once true power is not equal to measured power because of pressure coil inductance. That is, whenever measured power is not equal to true power means there is some error is introduced in the measurement. That error we want to calculate. Now I want to discuss what is the error due to pressure coil inductance in a wattmeter. Okay. Yeah. All of you write down this error due to pressure coil inductance. Error due to pressure coil inductance. S. S. Now you know the expression for true power. Once again I am writing the what is the true power and what is the measured power. Okay. You know that true power equal to Vi cos pi by KRP S into dm by d theta. This you know, this equation already given. Then what is the measured power equal to? Measured power equal to Vi S cos beta cos of pi minus beta by KRP into dm by d theta. Okay, this you know. This is true power equation, this is measured power. Okay. Now first I want to define correction factor. Later on I will calculate the what is the error due to pressure coil inductance. First you define correction factor. Yes, correction factor equal to true power by measured power. Wherever we are calculating the correction factor, then you can define like this: true power by measured power. Then you know the true power equation, you know the measured power equation. You substitute here. S, this Vi cancel, KRP cancel, dm by d theta cancel. Then what you can get? Cos pi by S cos beta into cos of pi minus beta. This is the correction factor. Correction factor due to the correction factor for the error due to pressure coil inductance. That means here true power and measured power is not equal. To bring the true power is equal to bring the measured power is equal to true power, how much factor we can multiply. Okay, that is the significance of correction factor. To bring the measured power is equal to true power, because of error due to pressure coil inductance, then how much factor you can multiply? You multiply with this factor, cos pi by cos beta into cos of pi minus beta. What is pi? That you know, power factor angle. Beta is, that is angle due to inductance. Clear? Now this is correction factor we can use. Now from this we can extend this one, then we can get the error due to pressure coil inductance also. Tell. Shall you write like this? True power equal to S cos pi by cos beta into cos of pi minus beta into measured power. S, can you write like this? Then true power equal to cos pi by cos beta. Yes, cos pi by cos beta into cos of pi minus beta. What is cos of pi minus beta? You can write cos A minus B. Cos pi cos beta plus sin pi sin beta. Is correct? Cos A minus B, cos A cos B plus sin A sin B. Now from this you take cos pi cos beta is common into measured power. This is into measured power. Okay. Take cos pi cos beta is common. Then true power equal to cos pi by, you write cos pi into cos square beta. We are bringing this cos pi cos beta is common means this comes under denominator. Then what you get? 1 plus tan pi into tan beta into measured power. Okay. This cos pi cancel. We know that beta is very small because I told already, to measure the true power, pressure coil must be highly resistive. Highly resistive means we are designing the pressure coil with low inductance. If the inductance is less, what the beta is also less. Beta is very small. Beta is very small. If beta is very small, then cos square beta is nearly equal to 1. You take the beta 0, then cos of 0 1. You take beta is 0.1 or 0.2 or 1 degree or 2 degree, that is nearly equal to 1. That is the meaning. Cos square beta is nearly equal to 1. Then how to write this true power expression? Therefore true power equal to measured power by 1 plus tan pi into tan beta. Yes. From this, what the measured power equal to true power into 1 plus tan pi into tan beta. Tan pi into tan beta. Now from this, measured power equal to true power plus true power into tan pi into tan beta. Clear? Then from this, you tell me what is the measured power minus true power? Measured power minus true power equal to this, bringing this side, measured power minus true power equal to true power into tan pi into tan beta. Tan pi into tan beta. Shall you write like this? Measured power minus true power by true power into 100 equal to tan pi into tan beta into 100. Multiply both sides by 100. What this formula indicates? Yes, percentage error. This is the percentage error due to which one? Pressure coil inductance we are calculating. Yes. Percentage error due to, yes, percentage error due to pressure coil inductance. Pressure coil inductance is equal to tan pi into tan beta into 100. This is the percentage error due to pressure coil inductance. Very important 5-star formula that you concentrate. Here I want to write one more formula. From this I am writing one more formula here. What is the measured power minus true power? That is error due to pressure coil inductance. It is not a percentage error. Measured value minus true value gives the error. That is error due to pressure coil inductance. Therefore error equal to, how to write true power? Vi cos pi into tan pi, I am writing sin pi by cos pi into tan beta. Okay, cos pi cancel. Then what is the error due to pressure coil inductance? That is Vi sin pi into tan beta. Yes, Vi sin pi into tan beta. This is one more formula that you remember. This is error due to pressure coil index. Okay, this is the percentage error, this is the error. Yes, I am simplifying this one. But here I want to write one statement. If power factor is reduces, that is, if the power factor is low. If the power factor is low, what is pi? Increases. If the pi is more, what about the sin pi is also high? If the sin pi is high, then what is the error? Error is high. That means we are using the wattmeter at low power factor. We are using the wattmeter at low power factor. Then wattmeter gives the large error. For example, same wattmeter we are using at 0.8 power factor lagging, at 0.2 power factor lagging. Then at what power factor error is large? At 0.2 power factor lagging, error is large. For example, same wattmeter we are using at 0.8 leading power factor and 0.2 leading power factor. At what power factor error is large? 0.2 leading power factor only. That's why at low power factor error is large. If you use the wattmeter at low power factor, error is large. That's the reason why I think you know that in laboratory we have the two types of wattmeters, UPF wattmeters and LPF wattmeters. Yes, the same wattmeter cannot be used at a high power factor and low power factor, because at low power factor error is large. In order to reduce the errors at low power factor, we are using specially designed wattmeter. That wattmeter is nothing but a LPF wattmeter, low power factor wattmeter. Therefore, error is large at low power factor. Low power factor. It may be lagging or leading. Whatever may be, at low power factor, error is large at low power factor. Okay, that point to remember. Okay, this is about what is the percentage error due to pressure coil inductance and what is the error due to pressure coil inductance. Then what is the correction factor? All this analysis I given with the assumption of lagging power factor loads only. Clear? Note down. Quick. Yes, over. So this is about calculation of error due to pressure coil inductance. Now based on this, I want to give summary 2. I already given summary 1. I told already, if you want to concept, then like this you follow. Only for quick reference point of view, whatever the summary I am giving, that summary you follow. Okay. Then I am giving summary 2. Yes. The summary I am giving. This first I am giving for lagging power factor loads. What are the formulas I derived for lagging power factor loads? For leading power factor loads, how to write that I will explain. Yes. Tell. First one is, what is the deflecting torque equation? The deflecting torque equation equal to, this I already given. This is IP into I into cos beta into cos of pi minus beta into dm by d theta. S ip into I into cos beta, sorry, ip into I into cos of pi minus beta. Cos of pi minus beta into dm by d theta. Okay, this equation I already given. Okay, then for lagging power factor loads, what is the measured power? Measured power equal to Vi by KRP cos beta cos of pi minus beta dm by d theta. This derivation also already given. Okay, now measured power is proportional to cos beta cos of pi minus beta. Important observation, for lagging power factor loads, the wattmeter reading, the measured power is proportional to cos beta cos of pi minus beta. Measured power is nothing but that is the power measured by the wattmeter. This derivation I given with assumption of beta less than pi. This I given beta less than pi. We are assuming that the angle introduced by pressure coil inductance is less than load angle. Understood? Load power factor angle. Next, for lagging power factor loads, measured power is greater than the true power. The proof also already given. Measured power is greater than the true power. Then, what is the percentage? What is the correction factor? Correction factor equal to true power by measured power. That is cos pi by cos beta into cos of pi minus beta. This formula also I already derivation I given. That is the correction factor. Now what is the percentage error due to pressure coil inductance? Percentage error due to pressure coil inductance. How much you calculated already? That is tan pi into tan beta into 100. Then what is the error? That is error due to pressure coil inductance equal to Vi sin pi into tan beta. Error is large at low power factor. This also I give. Error is large at low power factor. Okay, this is summary 2 with respect to lagging power factor loads. Every point is important. What is the deflecting torque equation? What is the measured power? Measured power is proportional to, measured power is greater than true power. Because of measured power is greater than true power only, we are getting error is positive. Yes, error is positive. This is the correction factor. What is the percentage error? What is the error? Error is large at low power factors. Clear? Okay, this summary you concentrate. In summary 2, this is with respect to lagging power factor loads. With respect to leading power factor loads without derivation, how to write that I want to explain. Yes, for leading power factor loads. For leading power factor loads. I am talking about with respect to measured power. Okay, first you draw the vector diagram, then we get idea how to write the formulas directly. Leading power factor loads means let the supply voltage is V. The reference is supply voltage V. But always, what is the pressure coil current? Pressure coil current is lagging because pressure coil is having some inductance. This is IP, this angle is beta. But here we are assuming that leading power factor. Leading power factor means then load current leads the voltage. Load current leads the voltage by angle of pi. Now what is the angle between IP and I? It is not pi minus B. This is pi plus beta. It is not pi minus beta. This is pi plus beta with respect to leading power factor loads. Now you tell the directly. Then what is the deflecting torque equation? The deflecting torque equation TD equal to is IP into I into Instead of cos of pi minus beta, you take cos pi plus beta. Easy to write. That is dm by d theta. The reason is this one. For leading power factor loads, current leads the voltage. Okay. Now, what is the expression for measured power? Then measured power equal to S VI by KRP cos beta into cos of pi plus beta S cos of pi plus beta into dm by d theta. This you know. Therefore, measured power is proportional to, for leading power factor loads, measured power is proportional to cos beta cos of pi plus beta. Next, this formula I derived with the assumption of beta less than pi only. With the assumption of beta less than pi. Okay. Now, what is the measured power is great? Here, measured power is greater than true power we are getting. Then we can apply the concept here. If, for example, pressure coil inductance is increases, beta increases, pi plus beta increases, cos of pi plus beta decreases, then what about the torque? Decreases. What is the theta? Decreases. In this case, this is not a ideal case, it's a practical case. In this case, theta indicating which power? Measured power. Therefore, measured power is less than true power. Same concept I already explained for lagging loads. This is for leading loads. For lagging power factor loads, measured power is greater than true power because of pressure coil inductance. But here measured power is less than true power. This is the proof. Okay, next, fourth one. What is the correction factor? Correction factor formula is true power by measured power. Then what you get? Cos pi by S. Cos beta into cos of, it is not pi minus beta, you take pi plus beta because of leading power factor loads. Next, what is the percentage error due to pressure coil inductance? Percentage error due to pressure coil inductance. Percentage error due to pressure coil inductance equal to S tan pi into tan beta into, how to define percentage error? Measured power minus true power by true power into 100. This how much we are getting? But tan pi into, as it is we can get tan pi into tan beta into 100. But what is the difference here for lagging loads and leading loads? For lagging loads, measured power is greater than true power, na? Then error is positive. But here measured power is less than true power, na? If the measured power is less than true power means this is less, this is high, then what this value becomes? Negative. Measured power less than true power means error is negative. Next, what is the error? Same formula, but you can get negative sign. The reason that you know, because of measured power less than true power. Then error equal to minus VI S sin pi into tan beta. Minus VI sin pi into tan. Then at low power factor, error is large. Error is large. Okay, this you know down. Okay, this is summary 2 for lagging power factor. But don't think like this, sir, for lagging loads, you are telling that error is large at low power factor. But at leading loads, error is small. That is meaningless. 0.2 lagging also low power factor, 0.2 leading also low power factor. We are not talking about type of load. We are talking about magnitude of power factor. 0.2 lagging, 0.2 leading. Both are same, but lagging indicates inductive load. Leading indicates capacitive load. Both the magnitudes are same, na? Both are low power factor. At low power factor, error is large. Okay, that's why at low power factor, error is large. It may be lagging power factor or it may be leading power factor. The only difference is here error is positive, here error is negative. That is the only difference. Clear? Understand? Quick note down. Yes. Like this, we are getting the error due to pressure coil inductance. Okay. Then how to reduce the error due to pressure coil inductance? How to eliminate the or how to reduce the error due to pressure coil inductance? Okay, that you concentrate. Yes, it's over. Yes, you write as a note. Yes, error due to pressure coil inductance is reduced. Error due to pressure coil inductance is reduced. Inductance is reduced by connecting parallelly note down, by connecting a capacitor across a portion of pressure coil resistance. Okay, this is the method you can apply to reduce the error due to pressure coil inductance. We are getting there is some error due to pressure coil inductance. The error due to pressure coil inductance is reduced by connecting a capacitor across a portion of pressure coil resistance. How it is means, this you follow like this. Let this is current coil and this is pressure coil. LP is pressure coil inductance. This RP is pressure coil resistance. Is some load. Yes, parallelly note down, don't wait. Then to reduce the error due to pressure coil inductance, let this total is RP. This LP is pressure coil inductance. Let this total is RP is the pressure coil resistance. Across a portion of resistance, we are connecting the capacitor. Let this resistance is small r. This resistance is small r. Then what about this remaining resistance? Yes, this remaining resistance is RP minus R. RP minus R. Okay. Now this is the capacitance we can connecting across. This total is the pressure coil resistance, but we are not connecting total pressure coil resistance. Only portion of resistance only we are connecting. Then we can reduce the error due to pressure coil inductance. Now we have the one question, sir. Why only portion of resistance? Why not the total resistance? Why you are connecting a capacitor only portion of resistance? Why not the total resistance you are connecting? Yes, the reason is, I told already, to measure the true power, pressure coil must be highly resistive. That means we want to maintain the high resistance of the pressure coil. Then if you connect the total resistance of the pressure coil, then resistance will be affected. Then it is not possible to maintain the high resistance. That is the reason. That's why we want to reduce the error. At the same time, we want to maintain the high pressure coil resistance. That's why we are connecting only portion of the resistance. Second statement. Second doubt. Sir, why you are connecting across the resistance? Why not in series with the resistance? The same concept I already discussed in MI instrument. Okay, if you connect a capacitor in series with the resistance, if you connect the capacitor in series with the resistance, if this wattmeter is using for DC power measurement, then for DC, for example, this is pressure coil, and pressure coil resistance we are connecting in series with the pressure coil. Now we are using this wattmeter for DC power measurement. Once we are using this wattmeter for DC power measurement, then for DC at steady state, capacitor acts as an open circuit. Once it acts as an open circuit, then there is no closed path for flow of current, then meter cannot work. That's the reason why we are connecting across the resistance. Now, even though we can apply the DC now even though capacitor is open circuit, then there is a path for flow of current, then meter can work. That's the reason why to make the meter is universal. Don't connect the capacitor. Universal in the sense, in order to use for both AC and DC. Don't use the capacitor don't connect the capacitor in series with resistance. Always you can connect the capacitor across the resistance. Now the question is, to reduce the error due to pressure coil inductance, what value of capacitance you can connect? That is the design of capacitance value. That is to reduce error due to pressure coil inductance. To reduce error due to pressure coil inductance, what value of capacitance you can connect? That is the design of capacitance value. Then for that, the design procedure is similar to what I explained in the case of MI type instrument. For that, you write the Z equivalent. First you write what is the equivalent impedance. The Z equivalent equal to, yes, this is Rp minus R, this is Rp minus R plus J omega Lp plus this small r and c is in parallel. Small r in parallel with 1 by J omega. Clear? This total impedance I am writing. This is Rp minus R, this is J omega Lp, these two are parallel. This resistance and this one is parallel. Okay. Now you simplify this one. Z equivalent equal to Rp minus R plus J omega Lp plus R into 1 by J omega C by R plus 1 by J omega C. Clear? Yes. Then Z equivalent equal to Rp minus R plus J omega Lp plus R by J omega C into R plus 1. Okay. Then to simplify this one, multiply and divide by complex conjugate. What is the complex conjugate of this one? 1 minus J omega Cr. That is 1 minus J omega Cr by 1 minus J omega Cr. Yes. Then what is the Z equivalent equal to? Z equivalent equal to Rp minus R plus J omega Lp plus R minus J omega C R square by 1 plus omega square C square R square. Now in this case, omega square C square R square very much less than 1. Why omega square C square R square is very much less than 1 means, whatever the capacitance we are using practically, this is in picofarads. C square in the sense that gives a very small value. That's why I am neglecting this one. Picofarad means 10 to the power of minus 12. 10 to the power of minus 12 square means 10 to the power of minus 24. That's why here I am giving approximate analysis. For approximate, I am neglecting this one. Then what is Z equivalent equal to? Rp minus R plus J omega Lp plus R minus J omega C R square. Yes. Then this is minus R plus R cancel. Then what is Z equivalent equal to? Rp plus J omega, take L is common, Lp minus C into R square. In this, the purpose of designing this one is to reduce the error due to pressure coil inductance. To reduce the error due to pressure coil inductance means we can equate this term is 0. This term, imaginary term is 0. Then to reduce the error due to pressure coil inductance, LP minus C R square equal to 0. Then what is C equal to? LP by R square. This is the value of capacitance we can connect. Important formula. To reduce the error due to pressure coil inductance, how much capacitance we can connect? C equal to LP by R square. Clear? Yes. But this formula I am deriving with the assumption of this term is neglected. Okay. Then this is approximate, not exact. This is approximate, not exact. Yes. But if you consider this term also, then you can get one quadratic equation. By solving that quadratic equation, we can get C equal to 0.41 LP by R square. Okay, this is exact formula. Exact. Okay, if both are given, you select the exact. Okay, this is the value of capacitance to reduce the error due to pressure coil inductance. This is approximate and this is the exact. Understand? Okay, quick note down. Like this, we can reduce the error due to pressure coil inductance by connecting the capacitor. Then what is that value of C equal to LP by R square, or C equal to 0.41 LP by R square. Quick note down. Yes, over. Okay, like this we can calculate the capacitance value in order to reduce the error due to pressure coil inductance. Clear? Understand? Okay. See, one more note I want to explain here that you concentrate. You also write one more note. We know that due to pressure coil inductance, for lagging power factor loads, what we are getting? Measured power is greater than true power. For leading power factor loads, what we are getting? Measured power is less than true power. Yes. For lagging power factor loads, we are getting measured power is greater than true power. For leading power factor loads, measured power is less than true power. This is because of the pressure coil inductance. But every inductive coil having its self capacitance also. That is called self capacitance or distribution capacitance. Because of that capacitance also, there is error in the measurement of power. For example, let us consider it is a pressure coil. This is pressure coil. The pressure coil itself will offer some capacitance. That is called turn to turn capacitance. This is called distribution capacitance of the coil. Okay, this is called turn to turn capacitance or distribution capacitance of the coil. This is CD. Let this is a distribution capacitance, capacitance or self capacitance of the coil. This is because of turn to turn. I think you know this one. Once we are manufacturing any inductive coil means, once we are preparing any inductive coils means, how we can make? You can take one core. On this core first we can place some insulation. On that insulation we are placing some turns. Okay. Again on that turn again we can place some insulation. Again we can make some turns. That means in manufacturing of any inductive coils there is a two turns or more number of turns are there. Each turns are separated by some insulating material. It's just like each turn acts as one conductor. It's just like two conductors are separated by some insulating material. Two conductors are separated by one insulating material means it acts as one capacitor. That capacitance is nothing but a self capacitance or distribution capacitance of the coil. That's why every inductive coil will offer the capacitance. Because of this capacitance also there is some error is introduced in the measurement. In the measurement of power using wattmeter. Then if you consider the error due to distribution capacitance, here no need of any calculation of error here. Mainly here one point to remember, due to self capacitance of coil also error is introduced. Then error in the sense the true power is greater than measured power or it may be less, or measured power is greater than true power or it may be less than true power. Then only there is error. If measured power equal true power, error is 0. But here error is there means whatever the power we are measuring that may be greater than true power or it may be less than the true power. Then when it is a greater than true power and when it is a less than the true power, exactly opposite. Because why I taken exactly opposite means the inductive reactance and capacitive reactance is opposite. If the inductive reactance is positive and capacitive reactance is negative. That's why exactly opposite we can get. Then for lagging power factor loads, this I am writing for lagging power factor loads. Measured power less than true power because of self capacitance of the coil. For leading power factor loads, measured power is greater than the true power. Here we can get error is positive, here we can get error is negative. But for lagging power factor loads error is negative, then for leading power factor loads error is positive due to self capacitance of the coil. Okay, these statements you remember. Understand? Quick note down. One more note you remember here. In general, wattmeter measures the power. Measure the power means there is some pressure coil voltage, there is a pressure coil current. Whenever there is a pressure coil voltage is exist, current coil current is exist, then automatically wattmeter measures the power. During power measurement, that wattmeter cannot see is it supply consists of harmonics or not. Whatever the input we can give, then wattmeter measures the power. But what power it can measure, I told already. Once we are talking about single phase power measurement, in general wattmeter measures the active power and it is a average power measuring and average power indicating meter. Understood? For example, if this is important observation to solve the problems. Okay, if V of t equal to V naught plus that is V of t equal to V naught plus Vm1 sin omega t plus theta 1 plus Vm2 sine 2 omega t plus theta 2 plus and so on. V0 plus Vm1 sin omega t plus theta 1, Vm2 sin 2 omega t plus theta 2 plus and so on. And I of t equal to I0 plus, here I am taking fundamental and harmonics also. Okay. If the supply consists of fundamental only, if the supply consists of both fundamental and harmonics, no problem. Wattmeter measures the power. Then which power it can measure? Average power. Then I0 plus Im1 sin omega t plus alpha 1 plus Im2 sin 2 omega t plus alpha 2 plus and so on is applied to yes, PC and CC of wattmeter. PC and CC of wattmeter. Pressure coil and current coil of wattmeter. Then the wattmeter reading is. Important observation to solve the problems. Then the wattmeter reading is. Then whatever the input you can apply to the wattmeter, then what value it can measure? Average one. Wattmeter is average power measuring and average power indicating. Then 1 by 2 pi integral 0 to 2 pi is V of t into I of t into d omega t. Like this you can calculate the wattmeter reading. But during solving of the problems, every time whatever the current and voltages are given, multiplying that one, integrating, substituting the limits is lengthy procedure. That's the reason why directly we can remember like this. Then wattmeter reading equal to average power. It measures the average power. Simplified formula I am giving. Directly we remember this formula during solving of the problems. Then V0 into I0 plus Vm1, you take this one, 1 by 2 Vm1 Im1 cos theta 1 minus alpha 1 plus Vm2 Im2 cos theta 2 minus alpha 2 plus and so on. Like this we can solve. Yes, V0 into I0 plus 1 by 2 Vm1 Im1 cos theta 1 minus alpha 1 Vm2 Im2 cos theta 2 minus alpha 2 plus and so on. Like this is the power measured by the wattmeter. But during applying this formula, you remember these observations. Okay, this is very important. Based on this formula, how to solve the problems, I will explain in the classroom workbook. Okay, but up to now, you remember this formula. If it is harmonics also given, only fundamental is given, harmonics also given, how to calculate the wattmeter reading is directly you can apply this formula. But during applying this formula, you remember these three observations. Here, I given this formula with the assumption of I taken voltage is sine and current is also in sine form. But during framing of the problem, we may expect sine cos or cos sine also we can expect. That's why if sine is during solving of the problem, if sine product is exist, you take cos. Even cos product is exist, then you take cos only. If sine cos or cos sine, both are same. Sine into cos or cos into sine, both are same, then you take the sine. But here this is theta minus alpha, this is also theta minus alpha, but here you take alpha minus theta. This is important. Okay, here if you take theta minus alpha or alpha minus theta, here no problem, because cos of minus theta will give the cos theta. But if you interchange here, then instead of plus we can get minus, then you get the wrong answer. That's why you take care about if sine cos product is came during solving of the problem. If sine cos product is came, then you take alpha minus theta. Okay, you take care about this one. Here no problem. Even interchange here no problem. But here you can interchange, instead of plus you can get minus, instead of minus you can get the plus. That is the problem. Okay, next one more observation. Here in the final formula the constants are multiplied and Vm1 Im1 is multiplied, Vm2 Im2 is multiplied. But if any problem is framed, which is Vm1, which is Im1, like that identifying is difficult. That's why simply you remember like this. In the final equation what we are getting? Vm1 Im only we are getting. Vm1 Im only we are getting means You see the reference is frequency. This omega is multiplied, then Vm1 Im1 we are getting. This 2 omega is multiplied, that's why Vm2 Im2 is we are getting. That means in the final formula you multiply only equal frequency terms. Even unequal frequency terms also multiplied, but by calculating that average value, that is 0. That's why again no need to do that one. That's the reason why if any problem is framed, you multiply only equal frequency terms. You multiply only equal frequency terms. If unequal frequency terms are given, no need to multiply that one because the average value of that becomes 0. That observation is also important during applying this formula. The another observation you remember, this formula I given with the assumption of theta is the angle given for voltage, alpha is the angle given for current. With that assumption I given this formula. But don't think like this, always first one is theta, second one is alpha angle. Like that don't think. Sometimes we may expect first I of t is given, next V of t is given. Okay, like that don't remember. That means here I given this formula with the assumption of theta is the angle given for voltage, alpha is the angle given for current. With that assumption only I explain. These observations are important during applying this formula. How you can apply this formula? In the classroom workbook, I will solve the problems. Later on that you will see. Okay, this is about actually based on this concept, single phase power measurement using wattmeter. There is 3 models of questions I want to cover. That 3 models of questions that you will see in the case of classroom workbook. Okay, with this, how to measure the power using wattmeter? What is the true power expression? What is the measured power expression? Then measured power is not equal to true power. What is the reason for measured power is not equal to true power? Because of the pressure coil inductance. Then what is the error due to pressure coil inductance? Then how to reduce the error due to pressure coil inductance? All these concepts I discussed. Clear? Okay. But I want to extend this one still in the single phase power measurement itself only. Not only error due to pressure coil inductance, there is an error due to connections also. I told already. In a wattmeter, there is 2 types of connections are exist. One is MC short connection, another one is LC short connection. Now I want to discuss in detail about what is the error due to MC short connection and where it is used. What is the error due to LC short connection and where it is used. And I want to discuss some points with respect to LPF wattmeter, low power factor wattmeter. With that, single phase power measurement will be complete. Then after that we can solve some classroom workbook questions. Clear? Concentrate. In the next session we will continue with the error due to connections. Thank you.